So pressure, stabilized Petrov-Galerkin and the least square on incompressibility constraints stabilized methods for higher order basis functions. Now we have our Stokes equation in the symmetric form. We have our stabilized methods in there. And the term that is new compared to the last video is this higher order derivative term. So let's focus on that one, and let's jump straight into the coercivity statement that we would get by considering that new term. So the new term is tau PSPG times the gradient of Q minus times nu times div symmetric gradient of V. Again, this is a non-symmetric term. We have even different types of functions in both slots. How do we go about treating this guy? Well, we have Young's inequality, which I'll write down one last time. Minus f comma g bound from below by minus 1 over 2 times epsilon times the norm of f square minus minus epsilon over 2 times the norm of g square. And now I'll use this inequality with the choice epsilon is equal to 2. So what do we get if we have that? Well, we replace this by this. Now, so this would also be true according to Young's inequality. Now additionally, I'm going to distribute my tau PSPG such a way that I have a square root on both sides. So I get square root of tau PSPG here and square root of tau PSPG here. And if I then use Young's inequality, well, then this is going to be bound from below by minus a quarter of the norm of the square root of tau PSPG on the gradient of Q and minus just the norm of the square root of tau PSPG. I don't know why I write it like that. Times, well, nu times the divergence. Well, this is getting a little out of hand. Let me move this down. Square and square. Okay, well, this first part is really not a problem. Remember that in the linear case we were left with this coercivity statement. But we still have half tau PSPG times the norm of the gradient of Q left. So we can simply subtract a quarter and we're still left with 1/4. So that's not an issue. Clearly this is the issue. What are we going to do with this term? Well, again, just like we saw with the SUPG estimates, we had this higher order term that involved diffusive terms, and we still have here this other diffusive normed quantity, and we would use an inverse inequality to link those two together. So that's again what we'll do here as well. So I'm going to try and bound this guy from below by the symmetric gradient of V and use an inverse inequality. So the inverse inequality is going to be that the norm of that higher order differential operator, and again we can do this per element, right? Because officially I had to break these integrals up into element-wise pieces. Excuse my abuse of notation. And we're going to say this is going to be bound from below. No, this is going to be bound from above by a certain constant independent of the mesh, our inverse estimate constant, by, well, a scaling with the mesh size, times the, and there's no squares here, times the norm of, well, just the symmetric gradient of that function. Also on the element. And again, the way that you would obtain this constant Ci is from an eigenvalue problem. And this is again sort of the inverse of a Poincaré inequality. Poincaré is trying to bound this guy from above by something like that. So the inverse estimate is the opposite of that. And as I said in the previous video as well, an inverse inequality is only possible due to the discrete nature of our function spaces, which is also illustrated by that scaling with h. If we have a very, very fine mesh, then this inequality is essentially limiting to an unbound inequality, which illustrates that in the limit case of h is equal to 0, where we essentially have our h1 Sobolev space, we don't have an inequality like this. So we use this inequality to replace this term. Well, what do we end up with? That's going to say that this term, this guy, together give me something that is bound from below, right? Because we have this minus sign, so that flips our inequality sign here by the square root of tau PSPG times CI h minus 1 times mu times the symmetric gradient of V. Okay, so that looks a lot like the term that I already had, which was nu times the symmetric gradient of u. Wait, sorry, that was a mistake here. This is a square root. Okay, I had the square root before. No, I didn't. Ah, here it was. So now I'll choose my tau PSPG in such a way that I can actually combine this term with that normed quantity that I already had. And the choice that we'll make is tau PSPG is going to be equal to, well, half of h square divided by Ci square divided by nu. Yeah, so if I make that choice, and I'm actually going to say this is going to be an upper bound, so my tau PSPG will always be smaller than or equal to that, and after that I still have room to choose. But if I make this requirement on tau PSPG, and then we can again say this is going to be larger than or equal to minus, well, what's left over here is really just the square root of nu, right? This one, this h square root cancels with divided by h. The Ci square root kills the Ci. Then we have still a square root of nu times nu gives just the square root of nu. And then I still have the half here as well. Times the symmetric gradient of V. Yeah, so that is half of the norm that I was left with in my previous analysis. I'm seeing now that this should be V. Just to be clear, the names of these functions don't really matter too much, right? It's a coercivity estimate is just saying that something has to hold for all possible functions, and whether I call that function U or V or P or Q is relatively arbitrary, of course. Yeah, so now we can see that additional term due to the higher order basis functions can actually be combined with the term that we already had and gives us a limit for our stabilization parameter. And the final coercivity estimate that we would then have is V, Q, bound from below by now half of the diffusive part plus, and then we only have a quarter left, remember? We have here minus a quarter of this one. We still had this one. So we only have a quarter left of, why do I write half if I'm saying that we have a quarter left? Times the norm of tau. I think I wrote it like this. Tau PSPG. And we didn't change anything for the LSIC part, so we still have half of tau LSIC times the norm of the divergence of V. Square. Okay, so again, this gives us an upper bound for our choice of stabilization parameter, but it doesn't specify anything other than that. We're going to have to make sure that we satisfy this, but other than that, we're left free with our choice. So we, again, just like for the SUPG method, our specific expressions for the stabilization parameters have to be based on something more than that, and that's where again the physics will come in via the subgrid scale modeling. Okay, so far the combination of tau PSPG and tau LSIC. I'll make one more video where we're going to combine everything, and we're going to combine SUPG, PSPG, LSIC, and we'll do this for the O'Sheen equation. Yeah, that's where we kind of left off before we started talking about the choices of stabilization parameters. Okay, thank you for your attention.